Orbital Gardens, this is Mission Control. We are confirming acquisition of your signal. You are live in 5, 4, 3, 2.
Hello and welcome to Gardeners of the Galaxy, the podcast for all of the sentient beings in the universe who have a passion for plants. I am Emma the Space Gardener and I will be your host as we explore gardening on Earth and beyond. Plants don't move, do they? We're used to the idea that plants are rooted in one spot, which botanists call sessile. But that doesn't mean they don't move at all, and we're used to the idea of them growing and turning towards the light, although those movements are usually too slow for us to catch them in the act. This episode started with a question: what were the first plants to fly on NASA's space shuttle? The answer to which takes us on a journey back in time to meet one of the world's most famous botanists. Before we get to that, I'd like to thank each and every one of you who supports the show, whether that's via a financial contribution or by sharing it with friends and colleagues. Gardeners of the Galaxy wouldn't exist without you. If you'd like to find out more about the different ways to help out, visit theunconventionalgardener.com/boosters. Now, if you'll join me in the time machine, we're just going to take a quick trip back to 19th century England, where a frustrated scientist is about to develop a shiny new obsession. In the summer of 1863, Charles Darwin, who had never benefited from robust health, was laid low by a ferocious bout of eczema. He was confined to his bed in Down House, and his normal work routine was disrupted. He passed the time studying the cucumber plants growing in pots on his windowsills, noting the circular motion of the shoot tips as they explored their environment, looking for supports to cling onto. He called these spontaneous revolutions circumnutations, from the Latin words meaning round and to nod. He asked his friend Joseph Dalton Hooker, who would later become director of the Royal Botanic Gardens at Kew, for more plants to observe. And as his health improved, he moved his studies outside and conducted experiments to monitor the plant's behaviour when he wasn't watching. Darwin thought he was making groundbreaking discoveries, but when he floated his findings to Asa Gray, a botanist at Harvard, he was brought back down to earth. Much of what Darwin had so painstakingly observed was already known to botanists. Darwin would have known that if he'd done some background reading. However, while the behaviour had been observed, it had not been explained. Darwin set out to understand how the plant was moving and why. To do so, he developed ingenious ways to record the movements of each part of the plant, creating somewhat bizarre diagrams that look like abstract join-the-dot puzzles. Darwin came to understand that as plants changed their position and grew into different shapes, they were displaying behaviour, not unlike that of animals, but at a much slower pace. In 1865, he published a monograph entitled On the Movements and Habits of Climbing Plants, in which he linked plant behaviour to his theory of evolution. His hypothesis was that plants were sensitive to their environment and used these environmental cues to guide their growth, thus surviving and reproducing more successfully. Darwin continued his investigations into plant movement with the help of his son, Francis, and together they published a book on the topic, The Power of Movement in Plants, in 1880. Darwin's studies uncovered the fact that circumnutation is incredibly common. It occurs not just in climbing plants or even just in angiosperms. It is seen in gymnosperms and some fungi and algae. Some colonial forms of bacteria exhibit remarkably similar patterns of movement. Circumnutations only occur in plant organs that are actively growing, and anything that interferes with growth inhibits circumnutation. The movement stops and starts, can be in either direction, and can even change direction. For some 50 years, the prevailing scientific explanation was that all of this movement was governed by the plant's growth system, including growth hormones and the gravity-sensing cells, statocytes, in the growing points. In 1967, however, Israelson and Johnson proposed a different explanation, arguing that circumnutations were driven and controlled by gravity. And so the two rival theories rubbed along together. The advantage of the gravity theory is that it can be tested, to some extent, with simulated gravity. Plant scientists can increase the gravitational force using centrifuges and use clinostats and random positioning devices to change the gravity vector. However, it's only really once you take a plant to space that you understand how much of its behaviour is affected by gravity. And this is where we meet Alan H. Brown. Brown was a biologist with a long career investigating the role of oxygen in biology. He spent a lot of time investigating the uptake and production of oxygen and carbon dioxide during photosynthesis, for example. During a stint at the University of Minnesota, he worked on the use of algae cultures to recycle carbon dioxide and produce oxygen for astronauts. He also worked with Professor Hiroshi Tamiya, a pioneer in mass algal cultures at Tokyo University, and was awarded a fellowship to work on oxygen exchange with algae with Professor Charles Whittingham at Cambridge University. Brown went on to become an early NASA consultant in space biosciences in the 1960s, and after moving to the University of Pennsylvania in 1963, he became a pioneer in studies on plant and human physiology in space. He was one of the original organisers, a founding charter member, and the first president of the American Society for Gravitational and Space Biology. His pioneering hardware for low-gravity research included a human-sized centrifuge designed to mimic the effects of space travel on astronauts. So with that CV, it's hardly surprising that he would become the principal investigator for the first plant experiments to fly on the Space Shuttle, and that's where he enters our story. On the 12th of April 1981, Space Shuttle Columbia blasted off for the first time on a test flight that would usher in a new era for American spaceflight. With more frequent spaceflights lasting days or weeks and a much larger astronaut pool, the Space Shuttle opened up exciting new avenues for space research. But this was uncharted territory, and the STS-1 mission was purely a test flight, an engineering shakedown to demonstrate that the shuttle system worked and could take people into space and safely bring them home. When Columbia launched again in November the same year, STS-2 was also primarily a test flight, demonstrating that the space vehicle was indeed reusable. But it also carried a modest, suitcase-like container quietly tucked into the crew quarters, and inside that case were the first plants to fly on a space shuttle. This wasn't even an experiment, but an engineering test to determine the optimum conditions for an investigation scheduled to fly on the first Spacelab mission. That would be the Helianthus Flight Experiment, or HEFLEX. The goal of HEFLEX was to answer one specific question. Are circumnutations driven by gravity, as the later theory suggests, or by something more innate, as Darwin thought? To test this out, the HEFLEX team had designed a plant carry-on container, or PCOC, which they referred to as Peacock, although there was no link to the flamboyantly feathered birds. But there was something they needed to check before HEFLEX could fly. Here on Earth, the relationship between the level of soil moisture and how tall new sunflower seedlings grow in 4 days was well documented, but Alan Brown didn't know for sure that it would hold true in space. So STS-2 flew a preliminary investigation called the HEFLEX Bioengineering Test, or HBT, which involved 88 dwarf sunflower seeds germinating in darkness and microgravity. Inside the Peacock, the sunflower seeds were packed into modules with different moisture levels, ranging from 58%, below which growth is minimal, to 80%, above which waterlogging inhibits growth. The sunflowers chosen were a commercially available dwarf variety called Teddy Bear that you may even have grown yourself. The original plan was for STS-1 to last around 2 days, which would have been too short for the HBT experiment. STS-2 was scheduled to last 4 to 5 days, which was perfect. However, after launch, Columbia developed a problem when one of the 3 fuel cells that produced electricity and drinking water failed, and the flight was shortened to 2 days. Although the research team were able to make some observations on seed germination and seedling development, this wasn't long enough for the HBT to reach a conclusion, and so HBT was given a refly on STS-3. Launched in March 1982, STS-3 lasted 8 days, which was longer than optimal for HBT. After the flight, the research team had to run a new ground control experiment to match unexpected temperature fluctuations recorded during the shuttle mission. Whilst the circumstances were not ideal, they were able to pin down a suitable moisture level for their future experiment. HEFLEX was go for launch. We'll pick that story up another day, but thanks for listening, and thanks again to my boosters for supporting the show. Don't forget that you can find the show notes on the website at theunconventionalgardener.com. You can also sign up to the Gardens of the Galaxy newsletter for new episode alerts and bonus astrobotany content. That's it for this episode, so I'll hand you back to Mission Control. Capcom, what's next on my to-do list?
Orbital Gardens, this is Mission Control. We're confirming termination of your signal. The ground control team would like you to rerun the radish cropping experiment. Apparently there was a bit of a mix-up with the samples you sent down, and the technicians had them for lunch. They did say to tell you they were very tasty.